Hi, in my previous video I repaired this Datron 7.5 digit meter model 1071, except the display, which is barely usable, especially these two blocks of special symbols. So in this video I'm going to attempt making a replacement for it, and my goal is to come up with a solution which would be reasonably cheap, let's say under $50, and repeatable by anyone in a similar situation. Let's go. Fortunately, there is a comprehensive service manual available with full schematics and descriptions of operation of every module, so no reverse engineering is needed here. Here is the description of the display module. It is divided into two sections, write mode and read mode. Write mode is about the main processor writing data into the display module, into this memory chip. And the read mode is about the display module itself, reading that data on a completely different time scale and driving the display. This control signal, let's call it select, comes from the address decoder on the main board. Each module in the meter is assigned its own address space, so that a particular combination of the higher bits on the address bus results in selecting a particular module the processor is talking to. So when this signal becomes active, it switches this selector, which is a two-way selector, the other side of it is not shown here, and it connects these lowest 4 bits of the address from the address bus to the memory chip. And the next pulse on this second control line results in writing the data from the data bus, whatever it was at the moment, into the memory chip at that address. And this control signal is marked phase to clock here, but it is used as a write signal. So, because only 4 bits of the address are used here, obviously this memory chip can store up to 16 bytes, and as we will see later, only 12 of them are really used. And here is the display we are dealing with. There are 9 decimal places and 2 blocks of special symbols. This decimal place is special. It can only show 1 and plus and minus. This is so-called half digit. Once meter reaches 2 in this decimal place, it means switching into the next range and shifting everything by 1 decimal place and losing 1 digit of resolution here. So why do we see 9 decimal places if this is a 7.5 digit meter? First of all, this decimal place is that half digit, which is extra, which leaves 8. And one of these 8 is taken at any moment in time by a decimal point. And because of this decision to have a decimal point and comma separately, we have 9 segments in each block, which means 8 bits is not enough for one block. So they decided to transmit commas separately. And 1 comma here is not used, which leaves 8, and that's the 12th byte. I mentioned before there are 12 bytes, 11 for each block, plus 1 byte for commas. And here is the description of the read mode with a diagram here. This is the same memory chip we've seen before. Here is a clock generator of 2 kHz. and this binary counter generates 4 bits of the address. This is the second side of the selector we've seen before. In this mode, the address from the counter is connected to the memory chip. The data goes to these buffers, and the output of these buffers is driving the cathodes of the display. And the address is decoded here and drives the anodes of the display. And here's a diagram for that special logic for commas. A particular address is reserved for that byte, which stores commas. When the counter hits that byte, the data is latched here and then is used together with the data for other segments to drive the appropriate comma. And here is the schematic. This is the memory chip, and this is the selector, which connects either 4 lines of address from the main board to the memory chip or 4 lines from this counter. This is the 2 kHz clock generator. These are 2 control lines. This is the select, and this is the phase 2 clock, which is used as a write signal, as I mentioned before. Here we have the data bus going through this buffer, and this is the latch for the commas. This is a decoder of the address going through this buffer to drive the anodes of the display, and these are the buffers for the cathodes of the display. So, how do we approach building a replacement for this? First of all, the simplest thing which comes to mind, and many people suggested it, is to hack the output circuitry somehow to drive 7-segment LED blocks instead of this high voltage gas discharge display. But I don't think this is going to work. First of all, because of the special symbols involved, and second, because of these non-standard decimal points, and they are not easy to remap to commas because they are also used as a part of letter R in error message. And remapping all that will take a microcontroller or something. Anyway, so I believe that a real approach is to hook up a microcontroller somehow, capture the data, decode, and send to some other sort of display, perhaps a graphics display, so any kind of symbol can be easily emulated on it. So, how can we hook up a microcontroller to this? I see 3 different ways to go about this, and all of them have their own advantages and disadvantages. The first way would be to start from the very beginning and essentially intercept that write cycle we looked at. There is a ribbon cable running from the main board to the display board, carrying these 4 address lines, these 2 control lines, and the data lines, as well as the ground and the 5-volt rail. So we could disconnect that ribbon cable from the display board and connect to our own microcontroller, eliminating this whole display board altogether and potentially reusing the space if needed. But the problem with this approach is the short time scale. That write cycle is about 1 microsecond or so, and I'm thinking about using an Atmel based microcontroller, some sort of Arduino compatible thing, and there is a reason for that. We will talk about that later. And I'm not sure this thing will have enough performance to deal with such short events. The second way would be to intercept the read operation inside of this display module, which operates at the rate of 2 kHz or 500 microseconds. So it is about 500 times longer than that write cycle. So there would be no problem with performance. And in that case, we don't really need these two control signals. We can just, let's say, read these 4 address lines, which change every 500 microseconds and stay the same until the next change. So we can arrange an interrupt from the change, let's say, and once that happens, we can just read the data. And there is a small complication here that this will be interrupted every once in a while by that writing operation from the main board. So the data will briefly change for that 1 microsecond or so. But I think that would be easy to deal with. Just wait for stable data for some period of time, slightly longer than that 1 microsecond write cycle. The disadvantage of this approach is that we will need to leave the display board in place. We cannot reuse the space, and we will need to solder wires to the board, which is a bit messy modification, which I would like to avoid. It's fine for one-off project, but not really fine for that solution I keep in mind, which would be easy to replicate by anyone who wants that. Or let's say turn this into a kit or something like that. I would like to minimize modifications like that, soldering wires all over the place and such. So the third way would be to read the output of the display module. And on the first glance, it seems like the smallest possible modification to the meter, because we will need to desolder the display in any case. And in this case, we just solder some other module instead, right to the same pins. But there are a few complications here as well. The first one is about the output voltages, which go from 5 volts to minus 175, and we will either need to shift that back to logic levels somehow, or modify the meter again. Let's say we can disconnect the high voltage supply, 180 volts, and connect that line to the ground. It's a small modification, and the output voltages will go from 5 volts to the ground. And this already sounds more complicated than the other approaches. But the other approaches have one more problem I didn't talk about yet. It is next to impossible to run a cable from the inside of the meter to the front panel. There is just one small hole behind the display. I can show it later. And this approach would solve that problem. There is no need to run any cable at all. But there are a few more complications. First of all, we will need more pins in our microcontroller. 11 here plus 9 here, 20 in total. As opposed to 4 plus 8 in case of intercepting the read operation, or plus 2 more for these control signals in case of intercepting the write operation. And this is not a big problem. We can certainly find a microcontroller with enough pins, or use a port extender or something like that. But there is one more difficulty. In these segment buffers, there are these capacitors in line which turn logic level signals into short pulses to drive the gas discharge display, and this can make reconstructing the data at this point a bit tricky without modifying these buffers somehow, which I would like to avoid. This goes against the goal of making smallest possible modifications to the meter. So, as you can see, all three approaches have their own problems, and it's a bit difficult to decide which one to prefer. I suggest we start with the first approach and see how it goes. And here is the problem with running a cable to the front panel I mentioned before. Have a look. This front panel board extends all the way up and down and to the right and to the left, and this edge goes into a groove in the top cover and the same thing on the bottom, so there is no way to squeeze any ribbon cable around this board. So it seems that the only way is through this hole on the back of the display. And imagine squeezing a ribbon cable like this. This is the cable running to the display board. So imagine running that through that hole and not interfering somehow with the replacement display. Or perhaps we could arrange a connector on the back of the replacement display board sticking through this hole, but what sort of a connector that must be to fit, I'm not sure. And here is the display module on the bottom of the unit, and this is the ribbon cable from the main board, and this is the output, which runs over here and then through this side board to the front board and to the display pins. So we could reuse this path at least to pass the signals from this connector to this connector and to the front panel board, even if we put everything else on that display replacement board. But this means one more module over here, at least some sort of an adapter to pass the signals through, and that's one more piece to worry about. But let's not worry about this right now. We can come back to this later. Let's focus on having something working. Luckily, I found this cable in a local electronics store with 16-pin connectors of exactly the same type as used here in the meter. So we can unplug this one, plug this one in, plug this end into the breadboard and get started. So here I've done basic preparations. I connected the power rail and the ground to the corresponding rails on the breadboard, passed them to the other side, and prepared these two bypass capacitors just in case. And I connected my oscilloscope to the control lines. Let's have a look. And here they are on the scope. The yellow trace is our select signal, and the red trace is that phase 2 clock, which serves as the right signal, as I mentioned before. And according to the service manual, the main processor is running at 800 kHz, which means each cycle is about a microsecond. And sure enough, we have half a microsecond per division, so here is our microsecond. Let's zoom in a bit. So yeah, here it is, slightly more than a microsecond. And if we look at the schematic, it's not difficult to understand that the data is supposed to be written into the memory chip on the rising edge of that phase 2 clock, which means here, close to the end of this cycle. So how do we want to deal with this in our microcontroller? I think the best way would be to have two separate processes, just like our write cycle and read cycle described in the service manual. So one process would capture this data and store it somewhere, and another process would use that data to refresh the display. So the main loop should be that slow process of refreshing the display, and this quick event should be driven by an interrupt from the select signal. Let's zoom out to have a look at the bigger picture, and let's turn off this clock signal. So here are the select signals, or write cycles in other words, which come in some packets from time to time. And if we go back, here I noticed some sort of short glitches after each write cycle. So when we zoom in again and turn on the clock again, we can see that these glitches don't overlap with the rising edges of the clock at all. So in the meter they should be of no consequence, I believe. But in our case, when we are going to drive our interrupt from this signal, it might be a problem. But I think there are ways to deal with that problem. We will see. Here I arranged the very minimum to get started with testing. We don't really need any Arduino boards to use the Arduino development environment, just an Atmel microcontroller. I'm using Mega 328P here with 20 MHz crystal for the maximum performance of this family. And here I connected my USB programmer to a so-called ISP port, which stands for In-System Programming Port, and it is connected through an adapter like this. I made them myself. This is a 14-pin adapter, and that one is a 10-pin adapter. So here I connected the select signal to the interrupt 0 pin, and here I connected another channel of the scope to port B pin 0. I'm going to send a pulse there once we receive the interrupt, so we can see the timing on the scope. Here is the Arduino development environment. I selected Arduino Mini board, which uses Mega 328, and I selected USB ASP programmer. And here we have this interrupt handling routine, which only toggles that pin, port B0, and nothing else. We have nothing in the main loop, and here in the setup routine we have, as you can see, commented out touch interrupt 0, because this way happens to be way too slow. It introduces some levels of indirection, and I can show you later on the scope how slow it is. And I'm doing the same thing using these low level commands instead. This one is to configure the interrupt 0 on the rising edge, and this one is to enable interrupt 0, and this command is to configure that pin PB0 as an output pin. Here is what happens with that touch interrupt method. The interrupt happens here on the rising edge, and this is our pulse on port B0, and it is about 2.5 microseconds later. This is not acceptable at all. And here is what happens with the low level of attaching the interrupt. Let's zoom in a bit. As you can see, it is much faster, but still the pulse on port B0 is at the very end of this write cycle, so I'm not quite sure this will do the job. Here is another trick we can do to improve the performance. We can declare this interrupt routine as naked, and this means the compiler will not add the usual prologue and epilogue to this function, and that will save some CPU cycles. But we will need to worry about saving some registers on the stack ourselves, and once we start doing something meaningful here, we will need that for sure, and that will take back some of the saved time. But for now, let's see what's the absolute best performance we can get. And here it is. I believe this is the absolute best we can do with this microcontroller. And as I said, we will have to give up some of the saved time, so this may or may not do the job. So let's try capturing the data and sending it to some sort of a display. Let's talk about displays. I wanted something which would be almost as big as the original and not very expensive, and it should be not more than about 8 millimeters thick. So after a lot of searching, I came up with an idea of using several small graphics displays like this, side by side. And these are 1.44 inch TFT displays sold on eBay from China, and not only on eBay, and mounted on a board like this. They cost, let's say, about $4 or so. And this is great for prototyping, but for the final version we will need displays with no boards. And this way they can be found for less than $3. So we can use 4 or even 5 displays to cover this whole area and still be within, let's say, $20 budget. So we will need to put the same number of digits per display, and if we use 4 of them, and we have 9 digits plus special symbols, we will need to put 3 digits per display, so the digits will be slightly smaller than the original ones, and the last display will be fully dedicated to the special symbols. But if we use 5 displays, it will cover this whole area almost exactly. We can put 2 digits per display, and this way the digits will be even slightly larger than the original ones, but it will leave only half of the last display for the special symbols, and that must be okay, I believe, because there is some repetition here, like kilo ohms and mega ohms, microamps and milliamps in different blocks. And on a graphic display it will be put in the same spot. I bought a couple of them at different time to play with, and they look very similar, but they are very different because they use different controller chips in them. One is based on ILI 9163C, and another one is based on ST7735S, and they need different software libraries to support them, and both libraries, I believe, exist for Arduino only. That's why I said we need an Arduino compatible microcontroller. And I must say that I'm not very happy about the brightness of them and viewing angle. So they are not great, but barely acceptable, I should say. But I don't see any alternative at the moment, so let's give them a try. And here is the result so far. After a lot of experiments, mostly with software, it is almost working, but unfortunately not quite. Sometimes I see some garbage briefly appearing in one of these decimal places. It happens rarely, but it happens. Let me describe what we have so far. I connected the address lines to port C, pins from 0 to 3, and data lines to port D, except one pin, because pin 2 on port D is taken by the interrupt from the select signal. I connected this data line to port C pin 4 instead, and it needs to be remapped in software, which is very easy. And these resistors here are to translate the logical levels from 5 volts to 3.3 volts for these displays. On these boards we have only 3 components. This is a voltage regulator from 5 volts to 3.3 and capacitor connected to it. And this is a current limiting resistor for the LED backlight, 10 ohms, assuming we connect this line to 3.3 volts, or if we connect it to 5 volts we need an additional 100 ohm external resistor. Because this interface needs to go only one way, from the microcontroller to the display, we can easily translate the levels using resistive dividers, like so. The values of the resistors can be slightly different, but the ratio should stay approximately the same. Here is the software. The display I'm using is based on ILI 9163C controller chip. Here it is initialized. This rotation is needed because it is upside down currently. Here I added disabling timer interrupts, because I think Arduino environment initializes timer 0 at least by default to support delay functions in milliseconds. I don't need them here, and I don't need any competing interrupts. Here I reserve 16 bytes of data. This is the main loop calling display data. We can look at it later. And this is our magic interrupt handler, declared naked and written in assembly language to optimize it manually. So, right at the beginning we are already 4 to 9 clock cycles from the event, and that is because it takes 4 or 5 clock cycles to enter an interrupt routine, plus the microcontroller needs to finish currently executed instruction, which can also take up to 4 clock cycles. This is to handle that short glitch we have seen on the scope. This command is to check if the select signal is still high at this point, and if not, we return doing nothing. Otherwise we proceed, and here I save a couple of registers and use them to read the address from port C and then data from port D. And here from port C we also read that one more pin which we need to remap to port D. And just before reading we are plus 6 clock cycles from the beginning of this routine. Here I send the pulse to port B pin 0 so we can see it on the scope, and at this point we have our data and we can do the rest with no hurry. This section is to save more registers. Here I save status register because some commands later modify it. And I save 2 more registers. This section is to remap that pin from port C to port D. This section is to save the result into that array of 16 bytes. And here we restore the registers and return. And the rest of the code is to display data. This function displays the 9 digits, no symbols yet. And this is to draw the segments of the first special digit, and this is to draw regular digits. Let's talk about the timing. As we have seen, when we enter the interrupt routine, we are at least 4 to 9 clock cycles from the event, and one clock cycle is 50 nanoseconds because we are running at 20 megahertz. And now we have 200 nanoseconds per division on the screen, so we must end up somewhere from here to here, so we should expect this much of uncertainty. And ideally, it would be great to synchronize with that clock to reduce the uncertainty, but I don't think this is possible. First of all, we are probably past that falling edge already, at least in some cases, and if we wait for that rising edge, it would be too late to read the data. After that, we can read the data before and then do some kind of checking. But imagine a loop reading 2 ports, 1 instruction each, then some instruction to check that condition, which is another clock cycle, I think, and then jump to complete the loop if needed. That's 2 clock cycles, so 5 clock cycles per one step, one iteration, and that's just too much to reduce the uncertainty. We cannot reduce this uncertainty because 5 clock cycles, again, it's more than a division, it's division and a half here on the screen, and this is just too crude. So I don't think we can guarantee that we can capture the data properly. It took me a while to catch such an event. Are you ready? Watch the first 0. So, how can we fix this? A couple of ideas come to mind. One is a crazy idea to filter this in software somehow. Let's say if a particular byte changes quickly from one value to another and back, we can ignore that intermediate value or something like that. This would introduce a delay, and it does not sound as a very clean and reliable way. Another idea is to add a hardware 8-bit register to latch that data so that it will stay until the next such event, and there would be no problem at all reading it. I might try something like this, but now I am tempted to try our approach number 2 we discussed before, which is intercepting the read cycle. Here is the display controller board. This is the input from the main board. This is the output socket, and here I soldered this ribbon cable with the socket at the end, so I can plug in my prototype right into here instead of the socket on the main board. And the pinout is the same. 4 address lines, in this case operating at 2 kHz, 8 data lines, 5 volts and ground, and the remaining 2 pins, which were used for the control signals, we don't need them in this case, so I did not attach them anywhere. Here are the wires under this piece of electrical tape. And here is the result. It works reliably, no problem at all. So now we know that at least this way we can get stuff working, and I don't quite like that this way takes soldering wires and we cannot get rid of the display board and reuse the space. but there is an advantage as well. We want to drive 4 more displays, and that takes 4 more pins to drive the select signals of each display. And before we had only 1 pin left, so we would need another microcontroller with more pins or some port extender or something like that. But this way we save 4 pins. 2 because we don't need to read the control signals, and 2 more we can save because we don't really need the 20 MHz crystal in this case. We can run at much lower frequency so that the internal 8 MHz oscillator is enough. This is the new version of software. Let me quickly show you the differences. Here I disable the regular interrupts and enable instead pin change interrupts from the 4 address lines on port C. And this is the handler of the pin change interrupt. Here we read the address from port C, and here we read the data using this helping function, where we wait for the data to stay the same for 10 iterations of this loop, and if data changes we start all over again in this loop, but if it stays the same for 10 iterations we return this byte right here. And note that in this case we don't need to remap that pin from port C to port D. So here we save the result into that array of 16 bytes. And finally, this command is to deduplicate the interrupts, because this triggers on any change on any of the 4 pins, and several pins can change at the same time. I found that we can have duplicate interrupts, meaning that when we return from handling one, there is another one waiting. So this command is to clear the interrupt flag before returning, which fixes that problem. And the rest has to do with displaying the data. I didn't change anything here at all. Here is one more step forward, just to make sure we know how to drive more than one display. And these are, as you can see, slightly larger 1.8-inch displays. They won't fit into the meter, but these are the only 2 of the same type I have at the moment. And they are based on ST7735S chip, so I had to change the library, and I also decoded the special symbols. And also note that we are running without the crystal now, using the 8 MHz internal oscillator, so those 2 pins are available for input or output. This is an experiment to validate, at least partially, the approach number 3, which is reading the output from the display board on the display pins. And I didn't want to spend time implementing it in full at this moment, but I did want to make sure I can reconstruct the data from those segment buffers. So I disconnected the high voltage supply, connected that rail to the ground, and here I soldered this wire to one of the segments, which is segment D, and it is the bottom segment in the digits, and as you can see it works just fine. I had to introduce a delay in the software since this signal is shifted in time. So we have this mixed input, one line from here and the rest of the data lines from here, and that's why we have this extra comma in the wrong place, because if you remember, the comma information is removed from these segment lines, and there is a special line for that. I didn't really want to fix it right now because it is just a proof of concept. And I am making some assumptions here. One is that there would be no problem reading those 11 address lines because they have only simple buffers. And another is that reading the other segments will be the same as reading this one. If I can read this one, I can read them all. And given these assumptions, it seems like this approach number 3 is doable as well if we want to go this way. This is the approach number 1 again, but with the hardware 8-bit register to help the microcontroller. As you can see, we are running at 20 MHz again, and here is the 8-bit register. I'm latching that data on each rising edge of the phase 2 clock. There must be plenty of time for the microcontroller to read that data until the next rising edge. This way it seems to work reliably. Let's have a look at the software. There is a small change to take advantage of that hardware register. Here in the interrupt handler, we read our address from port C as soon as we can. And after that, there is this loop to wait for the rising edge of the write signal. And once that happens, our data is latched in the register, so we read it here, except one pin. And when we remap that pin, we use pin B0 instead of that pin in port C, because we read port C early. And here we are reading from that register, so the data is not going anywhere. And the rest of the code is exactly the same. I hope this was a comprehensive enough analysis of different approaches I could think of. I'm sure someone can come up with some other approaches, or at least variations, which may or may not be better in some aspects. The video is getting too long, and some parts did not arrive yet, which I needed for the next steps. So I am going to stop now and publish this as part 1. In the next part I am going to decide which way to go for the final version. If you like this part, consider subscribing so you don't miss the next one. If you want to discuss it, the link to the topic on the EV blog forum is in the description. Thanks for watching. Bye.